Good morning everyone, welcome to today's worked exam answer video where I'm having a look at an AQA A-level reactions of metal ions in aqueous solution question, where the metal ion we are focusing on is the aluminium 3+ ion. We've been given a little bit of a schematic there, so we're going to be looking at three different reactions of that aluminium ion, starting with the hex-aqua aluminium complex. The first three questions are asking us about those three reactions, and then we're also being asked to explain why a solution containing said hex-aqua aluminium ions has a pH of less than 7. So why is it acidic? So I'll do my annotating and then I'll come back and explain how to answer each of the questions. Okie dokie, so we've got three different types of reaction going on here. The reaction with the Na4-EDTA, or the EDTA 4- ion, to give us this colourless solution is an example of ligand substitution. The monodentate water ligands are going to be replaced by the 1-EDTA molecule, and in that question we're asked for the formula of complex A, so the formula post substitution. The reaction with the sodium hydroxide has the OH- ions acting as a base. They're going to take protons from the water ligands until we get a neutral substance being made, which is the white precipitate. When we then continue to add more base, that's when we then get a colourless solution forming, because the complex will then become charged once more. And we need to be able to write an equation to show from the starting point how we get to the formula of the colourless solution, and we need to explain the fact that we have to have an excess of the hydroxide ions for that to happen. The third reaction is then with our carbonate ions, and 3+ metal ions, so the aluminium 3+ and the iron 3+, react with carbonate ions in a different way to how iron 2+ or copper 2+ ions react with the carbonate ions. So the aluminium hex-aqua complex ion will donate protons, and those protons will react with the carbonate ions to give us CO2 and H2O, in addition to the white precipitate, which is the same white precipitate as is formed when we add sodium hydroxide, because the protons come off the water ligands to form hydroxide ion ligands until the charge goes down to 0. So let's look at the questions specifically next. So the question starts with the formula of the white precipitate. So we had 6 waters. 3 waters then each lose a proton. That takes us down to 3 hydroxide ion ligands. Why does that happen 3 times? Because the initial charge on the complex is +3, and each of these hydroxide ion ligands has a charge of -1. So this is when this becomes neutral, and when it's neutral it precipitates out of solution. The other observation we see is the effervescence, and it's important we say effervescence and we don't say we've made CO2, because that's not an observation. We know CO2 is made, we see that because it effervesces, and that's the equation for that up there. The equation for the reaction in total is that you have the hex-aqua aluminium complex ion reacting with the carbonate ions to give us the white precipitate, the CO2 and the water. Now, with this topic, I don't recommend rote learning all of the equations. I think if you understand how they work, you can construct them from there. But I do think the balancing numbers in this one are particularly tricky, because we've got 2 lots of the complex and 2 lots of the white precipitate being made. So I do remember the balancing numbers in this as 2, 3, 2, 3, 3, but I don't remember the whole equation because I don't feel like we need to. And that's the same for all the reactions in this topic. If you understand what's going on, then you should be able to piece together the equations from there. So in part B, we're asked for the formula of complex ion C, which is the colourless solution that is made once the white precipitate then further reacts. So we would have our white precipitate, which would be exactly the same as the formula of B, but then because we've added an excess of OH, minus ions, we get the OH minus ion acting as a base one more time and taking away another proton from one of our water ligands. That gives this complex now a charge, and when it's charged, any complex will be a solution. It only precipitates out of solution when it's neutral. The condition is that we need an excess of the NaOH so that the white precipitate we initially make can dissolve or react again to then form this. And it's asking us for an equation for the reaction starting with the AlH2O6 Now it might be that you get asked to do it from the white precipitate to the colourless solution, or from the original hex-aqua complex ion to the solution. So here we're going to need a total of 4 hydroxide ions, each taking a proton from a separate water ligand, leaves us with 2 waters, 4 OH minuses, to the overall charge on the complex -1, and then we've got our 4 waters because each of the OH minus ions, as I wrote up here, acting as a base, taking a proton, is going to form water. Now that is not ligand substitution. I know it might look like ligand substitution because we could just be swapping the 4 OHs on and taking 4 waters off. That is not what is happening. The sodium hydroxide provides the OH minus ions which act as a base, and they are accepting protons. Okay. The blue part of the schematic diagram is an example of ligand substitution. So the EDTA is a multidentate ligand. One EDTA molecule can form 6 coordinate bonds. So we started with 6 monodentate water ligands. We only need 1 EDTA if it can form 6 coordinate bonds. So all of the waters come off, and the formula of that complex ion will be Al, brackets not essential, around the EDTA, square brackets are essential because we've then got a charge. The aluminium ion has a 3+ charge, EDTA is 4-, so that means the complex overall here has a charge of -1. And finally, we have to explain with the use of an equation why a solution containing aluminium hexaqua ions has a pH of less than 7. And as I said earlier, the aluminium 3+ ion and the iron 3+ ion both have pHs less than 7. They are more acidic than the 2+ ions of iron and copper because the 3+ ions are smaller and more highly charged. So in this case, our aluminium 3+ ion is small and highly charged, and that causes the OH bonds in the water ligands to be weakened, and that means that it is easier for a proton to then be donated, and as soon as something is donated a proton, it is acting as an acid. The more protons that get donated, the more dissociation we have, the larger the Ka value would be, and that's going to give us a pH of less than 7. And in terms of our equation, we need to showcase how one of the water ligands is going to give up a proton, which would turn that into a hydroxide ion ligand, and bring the charge down on the complex from +3 to +2, as that is negatively charged. And like I say, anything that is able to donate protons is going to be acting as an acid and thus have an acidic pH. If it was asking about the Fe3+ ion, you would say the same thing. By comparison, the Fe2+ ion and the copper 2+ ion are larger and not as highly charged, so the OH bonds in the water ligands are not weakened as much, so we have far less dissociation, so they are not as good acids by comparison, and that is why they do not react with the carbonate ions in the way that a 3+ ion will be able to. Hopefully that's helpful. It's a tricky topic, particularly if you don't understand the nature of the reactions going on, which I'll openly admit I did not doing my own A-level. Obviously I do a lot more now. If anybody has any questions about anything that I've said in this particular question, or if anybody has a similar looking question that they're struggling with, please get in touch by leaving a comment on this video, contacting me through social media, or dropping me an email, and I'll be more than happy to help. Thanks guys.